Good afternoon. This is Ping Wang from Nova 77 STEM Workshop. Welcome to this webinar series on Geology plus AI. Today is the third part of our four-part webinar series, and the focus will be on IODP expeditions and other scientific cruise expeditions, which provide the very important background knowledge for the IODP rock images we have been working on in the past 2 years. Our guest speaker is Dr. Kevin Konrad, who's an assistant professor at UNLV and director of the Nevada Isotope Geochronology Lab. Dr. Kevin Konrad has a lot of experience in scientific cruise expeditions. Kevin, thank you very much for being here with us and for sharing your knowledge and expertise with us in this webinar.
Yeah, thank you so much. Yeah, so today I'm going to give you an overview, kind of the International Ocean Discovery Program, which is kind of the premier ocean drilling science program in the world. And I'll give you some history on that, what they do, and some of the initiatives briefly for AI programming and big data science. And then I'll go into just a day-to-day operation, what's it like being on a drilling vessel, like the JOIDES Resolution, which is right here. So first, just an overview. So IODP, it's an international scientific community, and they're focused on interdisciplinary research from the sea, collecting samples from the seafloor. And so by international, I mean that there are many different countries that all collaborate to work on the same problems. Their main focus is looking at what connects the solid earth, ocean, life, climate, and society. So the bigger pictures of how can we explore the earth scientifically and benefit society. And they focus a lot on the interconnected earth. So there's certain things that we can only understand through collecting deep cores in the ocean basins. And since it's hard to actually get these cores, we focus a lot on interdisciplinary science, where we have biologists, chemists, geologists like myself, physicists, et cetera, all working on these samples to try to address problems from multiple angles. And so we mostly focus on looking into Earth's past by looking at the collection and deposition of different sediments and other archives through time. And finally, the goal of IODP is to communicate this knowledge to the scientific and global community through outreach programs. So, as I said already, the most important aspect of IODP is kind of to combine a diverse suite of disciplines to address large questions into the Earth systems. And these kind of come down to 6 different main topics, which we'll look at: the dynamic Earth, climate and the environment through time, how life has evolved through time, and then how that feeds into understanding natural hazards, cycles of Earth processes, and then health and habitability of the planet. So by dynamic Earth, what we essentially mean is how do we look at long-term variations in the Earth, such as volcanism, plate tectonics, earthquakes, volcanic hazards, and how does that feed into other aspects of the Earth system? When we talk about climate and the environment, we want to try to understand what are the long-term and short-term processes that govern global climate, and then how what causes tipping points and ecosystems, and how do environments react to changes in climate. And this is particularly important, of course, because we're on a current large change in climate across Earth on timescales that are unheard of in the geologic past. So we want to go back in time to when we had quick changes in climate and see how the Earth evolved around that. We're interested in life, and particularly the evolution of life by looking through paleontology as recorded in the ocean basins through times. Oftentimes we look at small microorganisms and how their productivity controls climate and relates to other Earth system processes such as erosion or volcanism. And then also we actually look at life inside of Earth's crust. So deep under the ocean, under the rocks that are beneath the ocean, there is life living inside those rocks. So we're interested in how those little microbial lives can live and form, and what kind of energies they can produce and consume. Now we want to use those three processes to try to understand natural hazards, of course. So we want to look at how things like tsunamis can change through times and earthquakes, and then try to use that observation to evaluate future risks, which is a main aspect of geology as a whole. So here's an example of a tsunami that went through a beach town. So we want to prevent these kind of things to the best of our ability. We're interested in cycles, and so the Earth as a whole is connected. And so we want to know what kind of rates and magnitude when we have outgassing at, say, a hydrothermal vent in the ocean basins, how does that affect the whole ocean? And on very long timescales, million-year timescales, how does that affect climate, natural resources, and evolution? And then, of course, health and habitability. So we want to get critical information to try to see how Earth responds to natural and anthropogenic, which is a term meaning human-derived, disruptions to the life system on the planet. And so we want to understand future habitability so we can prevent things like coral bleaching, where coral colonies can get wiped out, or other things with an ever-changing Earth. So let's give a little bit of history now on scientific sampling. So the first actual seafloor samples were collected back in the 1870s. Well, the first seafloor samples were collected by Darwin on board the Beagle prior to this, but they just kind of pulled up some samples with buckets and grabbed some sediment off the ground just because they were curious what's down there. The first actual dedicated ocean exploration campaign was by the British using a HMS, Her Majesty's ship, the Challenger, and it was John Murray and Charles Thompson back in the late 1800s. And they went pretty much all around the world, and they did a lot of amazing stuff. So here's a painting of their ship, dramatically fighting waves, as all ship paintings are. And on board, they had an actual full chemistry lab here where they had microscopes, they had various jars for preserving things, and where they can describe and draw, and a few other chemical analysis. And then for sampling, they had a variety of different tools. So they actually had some dredging mechanisms. So right here was a early type of dredge, which they would basically just drag on the bottom of the ocean, and they'll see what they grab, any life forms, rocks, sediments. And so they can find basalts and other lava flow based samples from the ocean basins, which were all exciting discoveries. And then they had some devices they use to determine depth and pressure at depth. So they can go down to certain depths, determine the pressure, and see how deep the ocean was, and start mapping out. What they found was the Marianas Trench, which is south of Japan today. And that's the deepest area of the world. And they actually discovered that when they first put some of these tools down there. And it's named after the boat, the Challenger Deep, which is the deepest place on Earth, which is 11,500 meters below sea level, or 37,000 feet. So quite deep. Then back in, that was pretty much it up until the early 1940s. So the 1940s, because of World War II, we invented the means to actually map the bottom of the oceans. And we did that to try to find German submarines, but it turned out eventually that we can use it to map the ocean basins and use it for science. But we also made piston cores. And what that is essentially is, here's an example of one. So this is the seafloor here. And then in blue, here's the ocean. And what we do is we drop off a ship a super heavy weight that's attached to this big hollow tube. And then that hollow tube is attached now to this little trigger here. And that trigger has this little gravity, basically another heavy weight right here. And what happens is the way this tension, there's a wire basically between this part of the core and this part of the weight that is super tightly wound. So it's very high tension. And then when this part of the weight hits the ground, before this core does, it pops up, releases that tension, and then it rockets this core into the ground. And because of that technology, they were able to actually now shoot cores deep into the ground of the seafloor and pull up long multiple meter long cores of the ocean basins. And so that now was first really utilized in any earnestness by a Swedish vessel. It was called the Albatross. And here's a picture of it, an old grainy picture. And it sailed around the entire world, and it collected meters of sediment cores. So a meter is about 3.5 feet. So many feet of sediment cores were collected by this ship, and they discovered a lot of great science right off the bat. They discovered that sediments, so how much actual little grains of mud and debris, it accumulates high away from mid-ocean ridges, and then mid-ocean ridges are barren and actually contain young rocks, it appears. They also did seismic reflection measurements, which is essentially what they did is let off little bombs in the ocean. And then they counted and timed how long it took for those waves of force from the bombs to come back up. And from that, they can get how deep the ocean was and how thick different sediment layers were in the ocean. And some of these evidence will become, some of these collections will become some strong evidence for plate tectonics, which is now that we know today is that Earth is composed of multiple plates that move around relative to each other. But at the time, that was very controversial. All right, and so that was, so some other coring expeditions, but we didn't have any really deep samplings of Earth's deep oceans for a long time. And that came Project MOHO, and I'll explain what that means in a second. But essentially, NSF, the National Science Foundation for the US, the government, they funded an attempt to drill all the way into Earth's mantle. So they wanted to go as deep into Earth as they can, where it gets hot and plasticky, and try to actually see what the composition of Earth is as it varies through that depth. So there's a guy named Walter Munk who proposed this. Conveniently, he was the head of the NSF's Earth Science Division and a few other places, so he had a lot of weight to throw around, and so he got it through. And it was considered the Earth Science's answer to the space program. So at this time in the late 50s, early 60s, we were competing heavily with the Soviets to try to put satellites in orbit and put people on the moon. And then we also wanted to now just outdrill them. They weren't really competing to do that, but we got to get on board, get that science funding. So it consisted of 3 phases. Step 1, they were going to drill using this boat here, the CUSS, the CUSS. And then they were going to go through and create a new program that can control the drilling. And then they were going to have this long-term event where you drill down 7 kilometers into the Earth's crust to hit the mantle. So what is MOHO? So the MOHO is a play on words for the Mohorovic discontinuity. And what that is at depth around under the ocean basins, around 7 kilometers, there's a really strong change in composition. So Earth's composition goes from being brittle and kind of dense and hard to a little plasticky and still dense and hotter. And so they believe this is if you remember from your science classes, this is the transition between the Earth's crust and Earth's mantle. So Earth's mantle is this plastic area of Earth at depth where it can flow and move a little bit, while the crust is hard and brittle, and that's what we're standing on today. And so they found out that there is this change in composition mostly from earthquakes by looking at seismic velocity data, where I won't go into the details of it, but how quickly an earthquake, the signals and ripples from an earthquake occur varies depending on the depth of the earthquake and where it penetrates from. And then if you look at enough earthquakes, you can start to build up maps of Earth's interior and see where that changes. So phase 1 was very successful. So this was all the way back in 1960, I think. They started off with Guadalupe in Mexico, and they recovered 5 cores. That got down to the deepest one was about 600 feet. So they drilled 600 feet of ocean crust, which is pretty neat. They recovered a whole bunch of sediments, and they recovered some underlying lava flow that was beneath those sediments. Here was the ship, the CUSS 1. John Steinbeck, famous American author, described it as having the sleek race lines of an outhouse standing on a garbage scow, which is a fancy way of saying it looked like an outhouse on top of a garbage boat. And it was an ugly ship, and that's his way of saying it. Unfortunately, phase 2 never began. So the program ran into a lot of issues. There was a couple of things. A, the government wanted to focus on the spaceways because the Soviets successfully put Sputnik, the first satellite, into orbit. And then more importantly, there was so much infighting between the different scientists and some government agencies that they couldn't get a successful leadership going and couldn't get a clean, well-run program. And so D.S. Greenberg, who was a science journalist at the time, described it as a lengthy and unattractive trail of bickering, bitterness, and short-sightedness, and involving some of the leading figures in American science and science administration. So it's also it's a nice reminder that when you're dealing with science, you're dealing with humans, and humans have a long and unattractive history of bickering and bitterness and short-sightedness. So they ended up kind of crushing their own program. On top of that, it cost a lot of money and they went way over budget. But that being said, despite that project getting canceled, this entirety of the recovered cores was incredibly important for showcasing that we can drill into the ocean crust and basins and recover rock samples. And so here is some of the samples recovered from that expedition, some of the lighter sediments and some of the basalts from the deep sections. Here's a scientist at, I believe this is Woodsall Oceanographic Institute in Massachusetts. And so on the one hand, the project failed, but on the other hand, ocean drilling succeeded very strongly. And so in 1966, NSF and at the time, the University of California kind of signed a contract to work together. And they initiated what was called the Deep Sea Drilling Project, DPSP, sorry. Yeah, it should be DSDP, sorry. Based out of San Diego. And this ran until 1983. And they used this boat right here that was built in Texas, the DV Gloma Challenger. And that boat was used up until 1983. And it's a significant improvement over the Cuss in general. So right off the bat, the first three expeditions already completely changed what we knew of geology at the time. The first two expeditions discovered that salt domes, so thick areas of salt basically in the Gulf of Mexico, in the seawater there, they can actually trap oil. And then that would then go on to be one of the most profitable areas for US exploration. That's where we still pull most of our oil that drives our cars and planes today out of the Gulf of Mexico. And so they discovered that how those were trapped. That was not the goal necessarily. The IODP, I should say, in this drilling program was never once designed for any economic advancement. It's purely designed for science, but they discovered this right off the bat. The third expedition, so in 1970, took a transit of cores across between leaving Rio de Janeiro, so here's South America, Brazil is about here. They left Rio de Janeiro, the capital of Brazil, and took a bunch of cores in between there and Africa. And what they found is that the cores, so here's the distance from, in this case, the Mid-Atlantic Ridge. And then here is an age that they got of the deepest sediments in the core. And what they found is they all got older as they moved away from this Mid-Atlantic Ridge. And that this Mid-Atlantic Ridge was actually the largest volcanic system on Earth, producing new crust. And that was the essence of plate tectonics, and it cemented it as a theory that we still work with today. So that was the third expedition. It was already very successful. So in 1975, though, it's very expensive to have these boats and do these expeditions. So instead of every country making their own boat because they want to get in on this cool science, it became actually an international collaborative effort that included in 1975 initially Germany, Japan, the United Kingdom, even the Soviet Union, and France. And so they all contributed money and then had people on the board of science exploration. And so we can actually work together, and every expedition can have scientists represented from each of these countries. I'll skip ahead a little bit just for now, but today, all the countries in blue represent partner countries for this expedition. So it's not every country because it still costs a lot of money. So it's countries with high GDP, but it includes all of Europe, including England, Canada. Of course, the US is still kind of the main contributor. Brazil, on and off, depending on who the president is. Currently, they're not as supportive, but they used to be more. Australia, New Zealand, India, China, South Korea, Japan, and a few other smaller countries. And so it's truly a collaborative effort, and it has been described consistently as the most successful international research collaboration effort, because it's still been going on since 1975, and it has not fallen apart yet. So it's been a very good, very strong, good faith relationship. Anyway, back to time. In 1983, the Gloma Challenger docked for its final time. It was old, it was falling apart. Instead of fixing most of the issues with it, they decided they're going to rebuild a brand new ship designed better for scientific exploration. And then they reorganized the program at the same time to simply called the Ocean Drilling Program. And the new ship was called Joides Resolution. DV means drilling vessel. And I'll talk about the Joides in detail because I sailed on it. So it was designed to do continuous coring and routine logging, so it can operate 24/7. So whenever it finds its spot, it can keep pulling out core at all times. It contributed to a lot of things, including climate change cycles, fluid flow, and they discovered the first microbial life below the seafloor. And just to give some examples of the kind of things, this is just in the first 3 years of the program. They drilled off of the Atlantic, and they found out exactly when and how the climate in East Central Africa became much, much drier about 2 million years ago. And that correlated with humans migrating out of Africa. And so they actually found out there was changes in climate that drove humans up into the Middle East and Europe at that time, which is crazy. In 1987, they drilled all the way down in 70 degrees south, so all the way really cold, close to Antarctica. And they discovered that Antarctica kind of formed its ice sheet relatively recently at 5 million years ago. And that's when it became permanent. This is near and dear to me because I'm a fan of this type of volcanism, but they also discovered evidence that hotspots, which are kind of melting anomalies in Earth's deep Earth that form things like Hawaii, so big volcanic islands like Hawaii are formed by these processes. And they discovered those processes can form islands for millions and millions of years. And it's one of my main research topics. And then they also discovered that the Himalayas, as the big mountains of the Himalayas in Tibet grew, that actually cooled the globe down, and that there's a long-term relationship between tectonic cycles like mountain building and global processes like cooling and heating. And then finally, they also, in 1989, using the ship, installed seismometers, so what they use to measure earthquakes, on the ocean bottom floor for the first time. And so now there's a lot of them in the ocean bottoms, and then what they do is they use it to track where earthquakes are and how frequently they happen. In this case, it was off of Western Japan, which is one of the highest earthquake-prone areas in the world. Anyway, that's just the first few years. I can go into every year, but we don't have time for that. So it became the Integrated Ocean Drilling Program now in 2003. And the reason it turned integrated is because now we were actually brought in new ships, and mainly the ship called Chikyu, which is a Japanese ship. And Chikyu was designed differently from the Joides. So the Joides is designed to take long cores and then move on. The Chikyu is designed to sit in the same spot for months and months at a time and drill the same hole as deep as possible. So the goal for this boat was just to make this big drilling platform here and drill as deep as they can. And they really wanted to get down into the earthquake zones off of Japan. It's one of the main reasons why they built it like this, to drill deep and understand why and when and where and what causes these different earthquakes in Japan. And then they changed the name to International Ocean Discovery Program. And that was mostly just nothing really changed that in 2013. They wanted to rebrand the name to emphasize that it's international in nature and that it's not related to any kind of oil exploration. So back in 2013, that's when things were getting more and more unpopular with the BP oil spill and other things. So they wanted to make sure people knew they're not a, drilling oil expedition kind of company, that they're a science expedition company. And so they're getting some complaints from people about drilling for oil, which they have never done, except the first expedition on accident. And it also became collaborative rather than integrated, which means now they work together. They work together more than it's just under the US umbrella with other people's funding. Now it's more collaborative with each government participating more. They have 3 ships, or 2 main ships, the Joides Resolution, which I'll discuss later, and the Chikyu, which I just showed. And then there's some mission-specific ships. So sometimes they'll get just ships with 1 or 2 expeditions that can do very specific things. And this diverse platform of ships allows them to address all the different kind of proposals they get. Anything related to drilling in the ocean, they can handle. Each boat has its own facility board. And when you go on an expedition for the JOIDES resolutions, you're pretty much at sea for 2 months every time. So that's standard. So it's a long time to be at sea. And then finally, this is up until a few years ago, each dot on this map. So here's a map of the Earth, Mercator projection. Each of these dots are different drill sites that they've had since the inception of DSDP until a couple of years ago. So they've had a few more sites since then. But they've covered the ocean basins really well, all over the place, except for White here. They've covered pretty much everywhere. And all these samples are available and still curated. So if you're ever interested in doing science, you can go and request a sample from this area, and it's still probably available today. So that's IODP up until today. They recently put out a framework describing what their goals are up until 2050. So they plan on drilling at least until 2050. And one of their 5 goals was technology development and big data analytics. So that's actually something they're very much interested in. Particularly, they're interested, and this is pertinent to what you guys have been doing, is machine learning images for core interpretations. And so here's an example actually from, this isn't from IODP necessarily, this is from a core of a type of rock called gabbro that was taken from Oman, so the Arabia, and there's a nice ophiolite sequence there. And this is from a paper by Peter Hopkins and others. And what they did was they took this image of it and they told it, all right, this gray stuff is what we know what it is. This is the gabbro. Can you find out everything in this core that's not gabbro? And so what they found is, have it map all these little veins of alteration products. And so here's the interpretation where anything that they think was gabbro is green. That's the base rock. Anything that's altered is blue. And then they can go in and try to pick out different minerals, like what is altered olivine, epidote, clinososite, zeolites, and color it based on what mineral constituents they think are in all these different veins. And then they can compare that, and they've used that relative to other things where they've scanned these cores for chemistry and did chemical maps of them, and then can see how the mineralogy changes based on those chemical maps through time. And so this is something they're really interested in IODP currently. And this is from their same book, the framework, that progress in ocean science drilling increasingly depends on the compilation and integration of very large and varied data sets, so big data, as we call it in the sciences, and using sophisticated computational tools to analyze them. And so I'm going to walk you through some of the aspects of day-to-day life on the boat, but just note that every expedition has 30 people, 30 scientists, and then a crew of maybe 10 people who assist the scientists, and then a crew of another 50 people who actually operate the boat. And so all of those people are working 12 hour shifts every single day collecting data. So anything we can do to increase the efficiency of data processing and data sets is highly valuable for IODP. All right, so I'm going to go through IODP Expedition 350 because I was on board it. Here's the little logo they made for it. We were looking at a subduction zone and unusual volcanism in the back of that subduction zone. There's me. I was a young, optimistic, dumb graduate student at the time, hoping to be an Argon geochronologist, which I am today, so it worked out. We started off in Taiwan, and I got to hang out there for a couple of days, and then we hopped on the boat. Just briefly, I'm not going to talk about the science or the science results from the expedition, but the goal here was here is Japan. We were looking south. Here's an arc of volcanoes south of Japan. And in the back of these volcanic arcs, there are these weird linear trends of volcanoes. And so what we wanted to do was drill right here in between 2 of these trends and actually look at how they evolve through time. So here's a seismic image, like I kind of said before, but so each of these little layers with different types of sediments. And the goal was, here was a seamount. So an old volcano was here, and there's a volcano here and here. And we thought this area would be a basin where all these rocks from the volcano would be collecting. So the goal was to drill into this volcano basin and collect as much sediment as we could. And the reason why is because we don't know how these little volcanic chains formed. This was like the main Tamara-san, who was the Japanese lead scientist on the expedition. His hypothesis was these chains of volcanoes formed from these convective cells in the mantle, making these fingers of like mantle material that come up and melt. But like I said, that's not the focus of this talk. Okay, so here's the droides from above, and it's composed of a variety of things. Here's the bow of the ship, which is the front. There's the big old anchor is right there. Here is some tables where you can hang out. Here's the bridge deck. The main living quarters was right here in the front of the boat. So my room was right here next to the anchor. So every 2 seconds, I can hear the anchor bang into the wall of my room, which was surprisingly comforting. It was kind of jarring at first, but you get really used to it. It's kind of nice. And then there's this drilling platform here. So this is actually, I'll show you where the pipes go up and then drill down. Then this is for all the science labs are right in this area. And this is all for just drilling operation over here. And then it has a little heli deck in the back. And people would jog in circles around this deck. I don't know how they did it. It was a very small deck. And all the exhaust from the boat came off right here. So it'd just be running into boat exhaust. And it was disgusting. All right. So here we are now on this part of the deck. And this is actually the main drilling implement. So this is just the bottom of it. Here is some people for scale. This is where the cores will go and go down through the boat into the ocean and drill deeper. If you look up, if you stand here and look up, you can see it's long pipes that go all the way up this rig right here. And here it is from a distance. So here's the drilling rig. This yellow tube here is the drilling unit that actually spins the pipe and drills down. And it can go up really high. And then when you're pulling up core, you need to go really high up because you collect tens of meters at a time. All of these tubes here, I don't have anything here for scale, but they're very large. All of these tubes here are the interior of each of those cores, and then these are the exterior. And you'll go through all of these through an expedition. So we drilled 1.8 kilometers of core from that one hole in the expedition. So we have to have a 1.8 kilometers of tubing. At least. At the bottom of the core is this right here. These are the actual little drilling mechanisms that grind up the crust and they build up friction and they grind a hole. They grind a hole, and then within that hole, you can actually push a tube through. And that's where your core, so your sample will go into here, and then around it will be ground out using these tubes. This here is Bubba, which is a great name for someone who's been with the program from the beginning. He's probably the strongest human I've ever seen. These things weigh hundreds of pounds and he can just like lift it. There is a gym on board with actual weights, and I just saw him just tossing up 90-pound shoulder presses like it was nothing, just for a morning warm-up before he goes to work. He was a crazy strong guy and a very nice guy. Here's Bubba again, but this time he's actually on his crane. So there's a big crane drilling implement that helps control this. And here's kind of the command center for that. All right, so now under what I just showed you, on the bottom side of the boat, this is what it looks like. There's a big moon pool here. So here's the ocean you can see from the center of the boat. And in this instance, this is the big drill tube that will go down to the bottom of the ocean. And the first thing we do is we use this little tool right here. And what this is essentially is a camera. And we have to take video images before we can drill. And the reason why is the ocean bottom actually has a lot of cables. So for like the internet, for instance, you know, say if you're in Australia, your internet actually comes from a different country. And those cables are run under the ocean floors. So there's actually a lot of cables that are run along the ocean floors. If we cut that cable, we cut out the internet for Australia, you know, for example. That is not good for an international collaborative effort. Most countries do not want their internet cut out. So the first thing we do is actually bring a camera down there and we we survey the floor, and we make sure there's no cables, there's nothing dangerous we can do, and then we start drilling. When we're ready to start drilling, we can drop this guy right here. So this is a big drilling plug, essentially, and here's the person for scale inside of it. And this is designed, so that's always going to be in the seafloor now. We drop that where we put the hole, and it's embedded now into the seafloor. And then every time we return to the hole to drill out more core, we have it here. And if we want to go back to the hole now, say today, so this was 2014, we can go back today, this would still be there, we can start drilling again. So that's kind of the design for it, to go back in future expeditions if it's really cool stuff you're finding. So here's that guy being dropped into the big old moon pool. It's kind of a ladder for scale. And so, let's see, how does this work? I'll show you a movie. Oh, sorry, it might make some sound. I don't know how to turn the sound off, so sorry if it's loud. Here is the crew actually loading up pipes and now drilling into the ground. So we're loading up pipes and we're moving it down, loading up pipes and we're moving it down. So remember, as far as distance, we have to cover, besides the fact that we're drilling 1.8 kilometers into the seafloor, we're also sitting 1,500 or 1.5 kilometers above the ocean floor. So we have to go through that as well. And so in this case, they're loading up a new pipe here. They connect it. And so they bring it all the way up the top of this guy here. And you can see all this space is needed just for these cores. They're so long. And now it's being dragged over. This guy just kind of ducks his head under it. And then there's where the actual core now is connected to the ground. And so now they run it into there, and they can drill it in, screw it into the connector. And it is rotating. And it's ready to go down. And so they'll do that for day in and day out. And there's other aspects which I don't have good videos for, but I would sadly, these poor Filipino engineers, I would stare at them for hours watching it because it was such a beautiful dance. Everyone knew their part. Everyone was in the right place at the same exact time, and they would just be loading up tubes after tubes after tubes, drilling down deep into the earth. It was really neat. Okay, so now we drilled up a core and we pull it back up. So the question is, what happens then? This is when now the scientists like myself come into play. So the first thing that happens is you'll hear over the loudspeaker very loudly, not in your rooms, but in any of the working spaces, core on deck. And then that means it's time to go into action for some people. This guy right here is the curator. He was charged of making sure everything was done correctly and curated properly. So these long PVC tubes are inside of those metal drilling tubes. And inside these PVC tubes is the rock that we're interested in, or sediment. I was an inorganic geochemist, and part of my goal was I would actually come up here when they first take the core, and they would take a bit of it and give it to me, and because I would crush it and squeeze it and analyze the pore fluids to make sure we're not hitting any methane seeps or anything that could be dangerous, which I'll discuss a little bit later. But right here at first, they mark everything up, make sure everything's neat and organized and consistent, and they break these long tubes into 3 meter sections. So they're easier and we can actually handle them. Then after that, you have to split those tubes. So right here, another video, so watch your ears. No sound on this one. We have these little core splitters right here, which are 2 little saws that come through and then they cut, boom, these 2 little cores. And now we have 2 halves. Every core will cut in half for 2 reasons. One, so we can actually see inside. Oh, and then any gaps we fill in with foam so they don't structurally become an issue. So the advantage of having both halves of these cores is one half becomes the working half. And that's the half I can actually take samples from and bring them back to my lab and do analyses on. The other half becomes the archive half, and that half never gets sampled, ideally. And that sample then will always exist. So whenever you need to go back and look at the core or do any kind of non-destructive analysis, so anything like take images or take certain scans which don't do any damage to the core, it's always available. So I can go back and look at the first core from DSDP, and there'll be an archive path I can examine. If it's a harder rock, so that was a sediment, but if it's like a really hard rock, like a lava flow, then we have this little guy here, which is essentially a tiosaur, a modified tiosaur that you cut it in half, because you have to actually cut through the rock. You can't just split it. And so then this is what you end up with. So you get a bunch of little cores of different sediments, different styles. Here's where different sediments we pulled up. And if you want to sample a sediment, you can put a little flag in it with your name on it. Can't really see, but there's like a 4-letter symbol for your name, and everyone has their own color. And then you fill out a request, say you want the sample, and you put the flag exactly where you want it. And then here's another example. So the first area it goes into here is the describing station. So there are multiple teams. In total, there are 30 scientists on board when I was on board. And there's a day crew and a night crew. So everyone works 12-hour shifts. So you're 12 hours on, 12 hours off. And one of the crews is the petrologists who describe these rocks. And so they'll look at them first and make their descriptions. Yeah, here they are. So here's an example of some of the petrologists standing around looking at a core that came up. And what's nice is you can actually have petrographic thin sections made on board, which is cool. So there's a cool, if you know what that is. If not, it's basically like a microscope slide with a really thin piece of rock on it. And you can figure out rock properties by looking at it. So they will describe the rocks. And then right behind them, I don't have any good images of it, sorry, but is a magnetometer. So it's essentially a big tube that you can run these cores through, and it can see what the magnetic properties are. And why that's important is because these magnetic properties are recorded when they were deposited initially, and they reflect what the Earth's magnetic field was doing at that time. So Earth's magnetic field that shields us from cosmic radiation and causes our compasses to point north, that shield flips in its orientation periodically through time. And so sometimes if you went back in time 750,000 years and you pull out your compass, it would point towards the South Pole, not the North Pole. And so we can actually use that to figure out roughly the age of our samples. Then there's a variety of microscopes and cameras on board. And so here's a petrologist describing some of the rock samples here and making notes. We make reports every week, tons and tons of reports. So by the end of the expedition, every aspect of the core is well described, and we can always go back and check that. We have biostratigraphers. Here's our American biostratigrapher here. And what they do is they look at the little microfossils that are inside the sediments, and they can say based on the presence of certain fossils versus the absence of certain fossils, roughly how old the sediments are. So we can kind of build an age model for the core through time. Now here's the more important place. So this is where I was. This is the chemistry lab. And here's all the great chemists I worked with. We had 2 lab techs here. And then Axel Smith, who was at UCLA at the time. Here's me, looking horrendous. Yang Yang from the Chinese Academy of Sciences. And then some other organic chemists from Germany and Japan. So remember, it's an international collaboration. And so that's where I spent most of my time. So we have a full, well, depending how you describe full, a large chemistry lab where you can do a variety of measurements. So here's the lab tech here. We have a variety of things for organic chemistry, as well as some solid state chemistry. We have an ICP AES, which is an inductively coupled plasma atomic emission spectrometer. And basically what that does is it creates a little plasma of the waters. We can extract waters from the core, and we can make a plasma of it and then examine the chemistry from that plasma. And what we do that for is for a variety of reasons. We can look at how the chemistry of the water within the sediment changes as a function of depth. But just as importantly, we need to actually monitor the levels of methane and a few other volatiles, because there are certain areas in the ocean basins where the volatiles are high enough where it can actually cause damage, like it cause a mini explosion from the friction and damage our drilling vessel. So there's certain areas we can't drill. We have to pull up if we get too high of a volatile content. Luckily, we didn't have that issue with our expedition. And then over here, we had a little handheld XRF. So the lab was not good at hard rock chemistry because they don't really have anything for identifying like basalts and gabos and lava flows and the stuff I love. But they did have a little handheld. Basically, this is a little handheld gun that shoots X-rays. And then based on the reflection of those X-rays, it gives you an idea of the chemistry. And the goal, and the reason why it's handheld, was to go through and just kind of zap rocks as you go. But it didn't work very well because it wasn't precise, for zapping rocks as you go. So we ended up building this frame for it and built a little station for it. So it became stationary and it worked much better. And we can make powders of our samples and analyze them. And it worked pretty well. Over here is an outline of the lab. So we had a balance on the lab. So what's nice about the ship, something I didn't mention, since we sit in the same spot all the time, the boat has a lot of thrusters all over it. And the first thing you do is you point yourself at the direction of the waves, so you minimize how much the boat moves. Then you have the thrusters that also minimize how much the boat moves. And the reason why you do that is because you want everything to be stable when you're drilling and doing work. And so you almost lose your immunity to seasickness after a while because it becomes so stable, you actually kind of forget you're on the ocean at times. And so, but since it's so stable, you can actually do things like weigh materials, which you can't do on a normal boat when you're just bobbing up and down in the ocean. We can heat stuff up. We have an oven where you can get loss of ignition data. You have a variety of other chemical tools, some spectrometers, some ion chromographs, et cetera, et cetera, et cetera. And so it's a pretty large lab. And then we have some stuff for organic biology, which wasn't on my expedition, a goal, but some areas we have to analyze things immediately after you pick it up because it'll decay and break apart quickly. And so what did we recover? So we started drilling, we got mud, and then we got mud, and then we got so much mud, constant mud. We actually pulled up about 1 kilometer of mud, and we were expecting little volcanic rocks. So that was, well, right off the bat, the seismic data did not match what we thought it did. And so we got tons and tons of mud. And then we finally hit an igneous rock. And as you can see, each of these stickers is a scientist saying they want this igneous rock. And so these became really fought over desperately. Here's me, Konrad. I wanted to try to date this rock, and I did. But everyone wanted a rock. So once we actually started hitting rocks, then there were stickers everywhere. Because another important point of this expedition is we didn't have a lot of sedimentologists on board because we thought we were going to get igneous rocks the whole time. And so even though we got a really fantastic 740,000 year record of sediments at high resolution, no one on board cared about it because we didn't have anyone on board who was interested in that. But eventually we got some cool rocks. And then we put all those stickers on it, and then we got pieces of it, and we can take those home and do analyses. And then after all of these rocks were done looking at them and taking out stuff, they eventually get shipped off to repositories where they're kept in giant refrigerators. So this is a giant refrigerator. This one is in Germany. There's 3 repositories that samples go to. There's one in Germany, Japan, and the US and Texas. And depending on where the core is taken, basically how close it is to any one of those repositories, it gets sent to those. And then each of these little boxes here is a core. And then there's just miles and miles of core everywhere you look. So all of them are always kept, since it's so hard and expensive to actually collect these. At any time, you can go back, a new scientist with a new method and a new idea can go and sample these and analyze them. And then, as I said, I'm not going to go into any details about the post-expedition work. I put out a nice little paper with Axel Smith on the chronology, and we managed to get a few argon ages. But as we got to a certain depth, the water there, that's actually the groundwater was so hot that I was resetting my argon ages, and so I ended up getting inverse ages. But that's besides the point. We got some data out of it. It was part of my thesis. It was very good. So let's talk about some other day-to-day life on the ship. So things can get fancy on the ship sometimes. During Easter, what they had is a massive feast. And each of the crew in the kitchen went and carved up some cool butter sculptures. And this monstrosity of a salmon fish, all edible with shrimp on it. And they made some seafood sushi. Here's some of the butter sculptures up close. They were really cool. This was for Easter, so I was there during Easter. Obviously, you can't leave during holidays. You work every day. Bunks were fine. This is kind of what your room looked like. What's nice is you get your room to yourself 12 hours a day. So when you're not on shift, you're allowed to be, you're in your room, or you don't have to be, but you're basically, whenever you're on shift, you're not allowed to go into your room. And that's because the other person has free reign. You're not allowed to just walk in while they're sleeping. So you're 12 hours on, 12 hours off. You have a little sink in your room, a little mirror. Bathrooms have 2 doors. So this is the same for any ship you're on doing expeditions. And so when you use the bathroom, you got to lock both doors. And then what's really important is this door goes to your neighbor's bunk. You can't leave it locked, because then they get locked out of the bathroom. They get really mad. So you have to make sure you have a good system where you don't lock each other out of the bathroom. Halfway through the expedition, we had a nice party. There's me all the way in the back, looking ridiculous. But we had a dance party. This is actually a little movie theater room. So it's a small little room where there was a big screen. And normally there's couches in here. And we can go and watch movies when we're not on shift. There's also a nice big gym I didn't have a picture of, but there's a gym where you can work out, lift weights, and run on treadmills. Another fun fact is if you sit in the boat in the ocean for 2 months in the same spot, you essentially become a reef, and you start growing things on the side of the boat, and you start attracting fish. So we were in the South of Japan, some of the most productive waters for fish. And so we had massive schools of tuna that would just circle around our boat all the time. And over here, we had bioluminescent squids and jellyfish sometimes. So I couldn't get a picture at night, but at night you'll get these blue glowing, fields coming through the ocean around your boat. And it was extremely beautiful. So now the question is, what happens if you get injured if you're at sea for 2 months? So there's a little medical office there and an actual doctor on board. So if you have any minor sicknesses, you can go and talk to him, and he'll help you. But this poor soul right here, one of the drilling engineers, broke his arm. So here he is with the head drilling engineer apparently laughing at him. And they just had to kind of rig him up. And what happened is we needed the Japanese Coast Guard to come and pick him up because he needed to go to a hospital. And so the Coast Guard came out and they flew over, but the helicopter was too big to land on our helipad. So actually this guy here had to rappel out and down to our boat. And then he had to package this guy up here on a gurney. And then he rode him all the way up back onto the helicopter. So there he is, strapped into this device. And here's the guy who helped him. And he rode him like a surfboard all the way back up to the helicopter, where he got loaded onto the helicopter then and taken to a hospital in Japan, where he was perfectly fine. And we had barbecues sometimes on weekends. Otherwise, the food was really good. It's just a lot of work. It goes super fast. It's super fun. Beautiful sunsets. Here's an example of a beautiful sunset with a few scientists staring at it. And I think that's about all I have for the overview of what it's like to be on an IODP ship. So I'm happy to take any questions. Hopefully I didn't go too long. Thank you.
Is there a way to drill by using equipment similar as a submarine, considering the weather may impact ships?
That would be great if we can. The hard part with the submarine is if you push it. So drilling with the submarine is one of our major goals. But anytime the force you take to actually push into something, the submarine gets moved backwards at an equal force. So unless there's a way you can latch onto a surface, you can't really drill with a submarine. What we want to do is take small cores of like igneous rocks using submarines. And what we've done is one of the expeditions I went on, there was a guy from NASA there, and he was interested in latching onto asteroids in space eventually to take samples. So he wanted to test out a device he made, which is essentially a giant claw. And that claw would grab onto the rock, and then you can drill into it using the claw. But it didn't work at that time. We're still working on it. That's kind of one of our goals. But to take miles, literally like 1.1 miles of core is what we took from this expedition, then we need something that can handle that much. And a submarine, there aren't any big enough submarines for that kind of work. Good question, though.
How long will one drilling process take?
It depends on how deep you want to go. So in our case, it took 1.5 months to get 1.1 miles of core. If you're taking just the top, so the looser the sediment, the faster you can take the core, because you're just kind of using gravity at that point to dig into it. Then you can pull up, I don't know, 10 feet every hour, essentially. So you can pull up a lot of core really fast.
How do you have access to fresh water on the ship?
That's a great question. We have giant tubs, essentially, that are parts of the ship are filled with fresh water, and then we have to refill it every expedition. So there is a limit to how much they want us to use it, but it typically lasts for all of our science purposes and taking showers and drinking and everything. It will last 2 months, no problem. And also in our kitchen, we have a soft serve ice cream machine, and we have some cappuccino makers. We have some cool stuff on board. So it's designed to be very comfortable while you're there for 2 months. But yeah, just a giant tubs basically in some of the bow of the ship.
What is the deepest hole these cruises have drilled?
Oh, good question. I think 5 kilometers is the deepest, but I don't know the exact number off the top of my head. So there is an attempt to go and drill into the mantle, which was the initial goal, which hasn't been directly successful yet. And the closest we've gotten is at a place called Hess. Was it Hesperos? No. I don't remember exactly where, but we've gotten pretty deep, and I want to say it's 5 kilometers, but I can't remember for sure. Part of the issue is the friction when you get to that depth is so high, it's actually physically difficult to drill.
That was a very thorough presentation. One of the questions my students asked was about the nature of technology advancement in drilling. How frequent is the technology updated for research missions? What are the main limiting factors?
Hey, that's a great question. Yeah, I don't know how often. It's not regular, but it is probably every 5 years or so they'll do some upgrades. The chemistry labs and labs on board, they'll be upgrading periodically. Essentially just to match, as technology improves, that match those. But as far as the drilling technology, they've had a few major renovations, and something like every 5 years to a decade, they'll have some kind of major renovations. And a lot of these result around, in order to actually drill out, these holes, you need to get rid of all the debris around the holes. So you have to actually pump fluids into it to blast out all the extra debris around the hole. So fluid pumping mechanisms are one of the limiting factors and one of the improvements they're trying to do. So essentially, whenever you dig a hole, you make a lot of debris around the hole. And so you have to get all that debris out so you don't get stuck. That's one of the major things. And then, as I said, one of the goals now is AI technology and programming technology, just to try to integrate all the data and efforts and try to automate things as much as possible so we can do more work at sea.
How do you decide where you would drill?
That's a great question. So you have to write a proposal. So there's basically the drill sites are decided by scientists who aren't necessarily part of this program. So like I right now, or Sichun, could write a proposal basically to go out to a specific area. And if we're compelling enough, we have enough information to say this would actually be of high scientific value to get samples from this area, then it will go to a board of people who assess it, scientific peers who read through it, decide if it's feasible, decide if they agree that this is of high value. And then if it gets approved, you can go out and drill, schedule your time. Before any drill sites actually go down, you have to actually survey the area first. So you have to go out with a different boat, collect bathymetry maps, seismic surveys, just to show that the area is drillable, and then you can go out and drill it.
Can I go on a scientific cruise?
Yes. So there are 2 positions, at least, that are not science related. They're called science outreach positions. And anyone can sign up for those if you have some kind of science outreach. So I see that it's Ping who said it, I think. So yeah, you can go on a cruise if you apply for one, and essentially you'll work a 12-hour shift and you'll control the outreach, which is you'll talk to schools. So any of the schools, like Ben's school here, can actually communicate with the boat while it's out there drilling and talk to the different scientists on board. if you want to set up a live Skype stream. And then you'll handle the Instagram page and other social media just to do reports. So there is positions for non-scientists.
We drilled to a depth of 500 meters at Detroit Seamount, hole 1203A. I am pretty sure this is not the deepest hole.
Indeed, it is not. No. And also, that might have missed Detroit Seamount. There's actually well, this is specifically for Shishun, but there's a controversy that might have hit crust and not seamount. But that's besides the point. Anyway, not much of a question.
Do people throw up or get seasick on the cruise?
Almost every scientist or everyone who goes out to sea gets seasick. There's a myth that like seagoing people don't get seasick. You typically get seasick for the first 2 days. And you take Dramamine or some other pills just to avoid that. And then you'll feel fine. Your body will adapt. There's a small minority of people whose body never adapts, and they're miserable. This expedition right here, it's not the first time I went to sea, but we pulled out of Taiwan, and it was going, I popped some Dramamine, which is a type of pill basically to prevent seasickness. And I threw up like crazy, like projectile vomiting. Sorry for anyone about to eat dinner. All over the place. And I thought, oh God, I'm getting seasick. I don't know how I'm going to do this for 2 months if I'm this seasick. Then I looked at the pill bottle and it turned out it expired 6 years ago. So I actually took some really old expired pills that made me super sick. And then when I went out to the doctor, he gave me some normal ones and I was perfectly fine. So I would just, as a warning, make sure Dramamine does expire and it's not pleasant when you have a bunch of expired Dramamine.